Anybody else want to record this? Okay. Okay, so we did adding big and small float numbers. And maybe next week we will review that, but I'm going to put it under the list of things already done. I'll show you my list in a moment. Except I don't have markers that work. Give me old stuff around here. So let's try again. Add big and small floats. Okay, I'm making a list so I don't forget. I don't want to teach the same thing twice. Okay, so. And then I think, class, that I did, what was the other one? Oh, there's a link inside of memory. There's a linked list of activation records. And I think I think I did it, demonstrated how you look at a memory dump and find the activation records in a list. Okay, and it's a little tricky, but you can master that. So I'm going to put on the completed list as find linked list of ARs. And it's kind of strange. They're linked on what I call the back end. The front end is the newest data in the activation record, but they're linked on their back ends. That's okay. That's been set up that way for many years. We'll just live with it. Okay, now how do you practice finding the list of activation records? I posted the same program I used to make that memory dump. I posted, I forgot its name. Let me find it. So that, what was it called? I think it was, well, here, let me find. I think it was called Stack Frames. You know, how can I tell you where it is? Practice. Okay, here, let's look at this. Yeah, you're right. I should be showing that. Okay, I'm trying to get the mouse wire out of the way. Okay, so I think this is done. And this is done. And earlier today, I posted the same program I use to demonstrate the linked list of activation records, posted program, program. And the way you find it is go to, oh yeah, at the class website, page number 4 is called subjects, like different subjects and different subjects in computer science. And under that, there's a page GDB, which I just started working on. It's kind of new. And under that, there's a page that's called Practice Program with 3 levels. Just program plus 3 levels. That's it. The 3 levels means main function calls first level calls second level calls third level. That's all it means. So if you want to practice for the program, for the concept question, there's a pre-made program. it has no application meaning. It doesn't solve any problem. It doesn't find the hypotenuse of a right triangle or anything. It's just a bunch of declared variables that don't do much. And so it's for practice using GDB, because at the very end, when it runs, it dumps out memory. And then you practice your skill of finding the linked list inside that memory. Okay. Be sure, in the source code, you can set how much memory you want to dump out. How does that go? I know what it's like. Show something. Show stack. And this is a function call from C++. And there's three integers here. The first one doesn't do anything. It's just a label. So the first integer is 300. That means when your stack dumps out, it's going to say this is stack number 300. You can put anything there. Okay. The next number is how many quad words you want to show that are not even in the stack. They're immediately outside the stack. And then the next number is how many quad words inside the stack you actually want to show, like that. It's up to you as user. You're free to manipulate those numbers, anything you want. Okay, so this is important. This is a number with addresses lower than RSP, and this is the number of quad words with addresses greater than RSP. So this is less than RSP. This is greater than RSP. Okay, let's see. Another item of announcement is our test is coming up. This is section 5. There's a test on May 12. And this is concept test. Starts 2 p.m. 2 p.m. to 4 p.m. That's regular class time. That's not a problem. May 19, 7 days later, 1 week later, this is programming. And 1 to 3 p.m. And I'm going to propose, unless somebody says I have a test schedule conflict, why don't we start at 12? How about 12 to 3? Okay, just like the midterm, it's supposed to give you more relaxed time. So it isn't high pressured. It's still pressure, but it's not, hopefully it's not as bad as if it were squeezed into 2 hours. Okay, so tonight, check your final exam schedule in your portal and see if you have a time conflict with that 1 hour before. If you do, maybe I can move you to another day of the week to do the test where there is no time conflict. Check it out. So check. Okay, let's see. Is there another now? Yeah, I got another announcement. This is a tough one. Okay. In fall semesters, you know, here's how the calendar works. In fall, we end the finals week ends around December 16 or 17. Somewhere around there, we're done with it. And the administration says we faculty have to turn in class grades January 2nd, usually, or a day after that, January 2 or 3. That's almost 3 weeks, 2.5 weeks to get all the stuff graded. But you know what happens in spring semester? This is really bad for your professors. In spring, you got 7 days. Spring semester. That's right now. Now, it's approximately 7 days to get it all done. And you saw how long it took me to get your midterm graded. Not 7 p.m. 7 days. Okay. So I have to make preparations for this. I'm going to go into electronic isolation when finals week on which day? 19th. On the 19th, after your test, I'm going to go into electronic isolation, which means I stay away from email and phones until all the grading is done. I don't live on anything else. I only just get up every day and just grade stuff from my 4 classes. Letting you know. So what does that have to do with the rest of you? Okay, a couple things. One is I'm not reading mail. You can't send me an update the next day. I won't see it until grades are already submitted. You got to send me your whole packet at the same day, like on the 19th, before 3 o'clock. You got to send me your whole packet complete. Send everything. I won't see the email if you say 6 hours later, oh, hey, I just discovered I didn't send you my bash file. Then it's too late. I'm not reading mail until your grades are in. Send everything, all the program files. A common error in grading the midterm was to edit the bash file in Windows, maybe Notepad or WordPad or some other tool. And then Windows puts CRLF line endings. If you edit in Windows, your bash file, unless you set it specifically to save as Unix files, it's going to add CRLF on the end of every line, and those bash files don't run when I get them then. Okay. You gotta check when you make that changeover, make sure you save your bash file. If you're editing in Windows, make sure you save as, I don't know the words they use, Linux compatible files. That means every file line ends in LF, line feed. That's one of the ASCII characters, not carriage return and line feed. These always crash. The program never gets compiled. The bash file crashes. This happens. It's not an isolated incident. And when I grade about 30 of you, there's 3 to 4 of them that the bash doesn't run. And I'm pretty sure it's the end of lines on them. Okay, so send me everything and check that it actually works. Check it. Here, I'll give you an example. This will get you more points. I don't know the person's name. I don't think it was in this section. A student enrolled in 240 makes a bash file, makes a program, and looks at the bash file and says, no, that's right. He told me I have to put my name and email address in here. So this person goes over to so here's bash. And here's the driver, C++. and says I got to put their name in there because the guy told me I have to. So copies the basic information about author and email and today's date and paste it over here and says I'm done. Sends me all the stuff, but this one crashes. Why does it crash? Because the comment lines over here are slashes. And this person copied comment lines right here into Bash. Bash saw that and refused to go any further. Says, I can't deal with this. What is this? That this person probably intended well, but when it got to here, didn't go ahead and run it one last time to see if everything was okay. Then it would have caught that. The comment line is a pound sign, not two slashes. Okay, so if you discover that the next day, it's too late. I'm not reading email after the end of finals week. But for us, not December, May 19. May 19, probably for the next 7 days to May 26, I'm out of it. Okay. Okay. I don't like it, but we've got a plan for it. There's great repercussions on faculty that are late turning in grades. Some get fired. What the administration called is their contract's not renewed. I mean, it's really severe. So I'm going to make the deadline. And here's the repercussions of it. You got to get it all together on the day of the final and send it to me as a packet. You don't have to zip the files, but just attach all of them, and that's it. There's no second run on it. Okay, you got the problem. I have a 270B final during the time. Yeah, Ricardo, you have it on May 19. That's our day. Yeah, hey, send me that in email and I'll send you back 2 choices. You can pick one of the 2. To the person asking me about that, just I'll work with you if we have time in advance like this. Okay. All right, let's go on to other things. Okay, so did I write this? Okay, I talked about that. Okay, and we did, I'm taking them off my other list. We'll come back and review this either Thursday this week or Tuesday next week. But I did lecture about it once. What happens when you add a big float to a small float? Usually the small float gets chopped off. And how to find the linked list when you have a memory dump. It'll take some detective work. It's not immediately obvious, but with a little careful, what do they call it? Sleuthing. You can find it in there. Okay. All right. What's else on my list? Let's look at, this whole semester we're studying hybrid programming. B-R-I-D. I think that's how you spell B-R-I-D. I hope that's it. Programming. We're mixing programming languages. Yeah, as opposed to pure programming where you have only one language, pure programming. Okay, so it was customary in old times, and even somewhat today, that faculty teach this. And I want to show you one example right now in the next few minutes. It is really a lot of work, because in pure programming, how does it go? You have no driver. You say, well, I can live without that. No, sure. Okay, but you have no pre-built functions written by someone else, no libraries. So that means you don't get printf, scanf. Did we do something else? I'm trying to recall. Get char. I don't know if we use that, but it's available. Anyways, there's no libraries usable if you're doing pure programming, and there's no functions written by you that are linkable in. No C++ or C written. These are written by, I don't know, they're not professionals. They're open source voluntary programmers, but there's no C++ written even by you. Okay, the whole program revolves around setting up, there's a block of code to set up for a syscall, system call. Things like that. And what syscall does is it calls a function that's already in the operating system. And I think the list is about from number 0 through 260. If you had the complete table of all the functions made available by the operating system, they're numbered from 0 to 260, approximate on the 260. And so you have to know the function you want to do, and you move it into a register. I think it's, we'll look it up in a few minutes. RDI, you move the number you want there, and you say syscall. Stands all by itself. And then that activates the function inside the operating system's kernel to do something like output a string or input a character. There's dozens of these. You do this kind of programming, you really need the table of all those syscall numbers nearby so you can operate, so you can build your program. That takes the place of all those library functions that we deal with. Here's my opinion. I found it very tedious, just worse than regular hybrid assembly. Very tedious, and you have to pay attention to, I never found you have to pay attention to such tiny details. I never found the syscall to input an integer. I hope it exists, but maybe it doesn't. I don't know. I don't know the code number to input an integer, so I had to input a string as an integer and then build my own what would be ATOI function. That converts from string to integer. There's one in the public library, but in pure assembly you can't use that one. That's not legal. You have to write your own. So I got to thinking, this is more work than I ever counted on. I want to input an integer, and here I have to look up a certain system call number, and then it only lets me input strings, so I have to input this number as a string and then make my own function to convert it to a regular integer. I never pursued that way of learning, and I don't teach that way, but there's a lot of faculty in California and the United States that teach pure assembly. It's the way they structure the class. You learn a lot of system call codes. Okay, so as a graduate of 240, you need to know that this style exists, even though I never teach it. Let me see. Yeah, Ricardo, I got, I'll look for your email. Okay, I want to show you one program and then we're going to pass on. You should go away from this course knowing that such a style of software exists. Someday oh, let's see. Oh no, you don't get away from having NASM installed. Oh, I see. You can program in an environment where there's no C++ and no C. If your computer system you're working on doesn't have those two languages and your system administrator won't install them for you in your workplace, you can still do assembly programming by calling upon the operating system to do the work of those functions. See how that's just a horrible way to work. Okay, we won't be long on this. Let me find where I can show you this. Yeah. Yeah, I gotta find where I saved one. I did one program in my life about this. Actually, okay. I'm going to share the screen as soon as I find the function, the file with this in it. Here it is. Okay, appear. Okay, I gotta move this to where we can view it. I found it. Okay, so here and here, and share the screen, the whole thing. Okay, so I think you're seeing my desktop.
Hey, Professor, I think you accidentally muted yourself.
Oh, no, I got it. I got it. Sorry, everybody. I didn't. I'm glad you tell me. I don't do that intentionally. I don't know how it turns mute on, but it did. If it happens again, tell me quickly. What I was talking about is okay. What was talking? Syscall replaces all the other functions you ever used in pure assembly, and you're looking at one sample program, and it has to have a starting name, which is called not main, but underscore start. that replaces anything like a main in a driver. Why is there's no backup registers? Because there's no caller. You see that? We're not pushing 15 R registers, because who are we trying to protect? This is the driver. And then there's a string up here called hello. So it's going to demonstrate how you would print F hello. And here's sample stuff. You put number 1 in RAX. Over here it says it's the number of the kernel function that we're going to call. Number 1 over here is a different number 1. That means send the output to standard output device, usually your monitor. And those are the setups. RSI receives the start of the string. R15 is the number of bytes in the string that you want to output. And then you say syscall. That's a printf on hello, if you want to make a comparison. And here's how you output a new line. Apparently I didn't have a new line on hello. See, if you look back here, oh, why doesn't it end in a 0? I don't even know that. I don't know, class. So weird to see a string terminate with no 0 on the end. Okay, we'll go on anyway. Okay, so the whole style is that way. Whatever you're going to do, you set it up, and then you say syscall, and it reads one of your code numbers, like usually RDI. No. Take it back. It's here. The first one, RAX, is the code number of the function in the operating system you're going to activate. A lot of syscalls. And I forgot what was happening here. Put something meaningful on top of the stack. That's a push operation. So I don't know how it got there, but oh, I'm sorry. Push is part of assembly. So it's legal to say push something. And I don't know what it's doing. Okay. So anyway, there's a real short program. The whole structure, if you're building a big system, the whole structure goes that way. I don't want you to learn this. It's not worth it. Modern programming in assembly that doesn't go into this pureness stuff. You don't have to be that sophisticated to get something done at your workplace. Can I close this? If you want to see the code, it's posted at our class website, but you don't have to see it. Okay, one last look at this guy. What's so different? There is no G++ compiling, and there's no G++ linking. Here's the linking. That's assembly linking right there without G++ helping us. The rest, it's all NASM. There's only one file. So there's one NASM, nothing else, no driver, and let's run it. It's kind of trivial, I think. Okay. So we need a terminal window. That's -L. Okay, sh run sh. That's all it did. I'll put a few messages. I had to write a lot of code to do this little piece here. All right. I'm going to leave it there. We took 7 or 8 minutes so that you could leave this course saying, I know that you can do assembly programming without the presence of the C compiler and without the presence of man, I can't get my words out. You can do assembly programming without C language and without C++ language. if you had to, but it's not much fun. Okay, I'm gonna change topics here in a very short moment. Oh, audio's gone. I'm sorry. Okay, let's switch. Where do I get it?
Professor, you're muted again.
I swear to God, I didn't. I swear to God, I didn't do it. But okay, glad you told me. I'm gonna talk about what's called inline assembly for 15 minutes. This is useful in a few specific cases. It's the case where you're working in the corporation environment, and most of the development is in a common language, but assembly is needed for like 0.5% of the lines of code in the big project. Just this tiny minuscule piece has to be in assembly. Maybe you're writing your team is creating a project of 40,000 lines of code, and someplace you need 10 lines of code because you have to access register RSP for whatever reason. Okay. It seems wasteful that you have to install NASM and set up a separate compilation of an assembly program of, say, 10 lines, and then link that into the big system just for such a small amount of work. In those cases, they use inline assembly, which means you have a C or C++ source file. And you got C language going on here, and then you insert a block of assembly, and then you go on and finish the C++ program. And the nice thing, they say, is you compile this with C++ compiler. You don't ever bring NASM into play. You don't even have to have it installed on your system. Okay, so I have one example to show you that. That is actually useful. I don't think it's the way to learn it in a teaching environment, but it can be useful in a software development company. Let's, I'll bring the example forward and we'll see it. If I go muted, feel free to tell me right away. Okay, so let's share the screen. I hope it's, let me make sure I'm in the right place. Yes, I am. Okay. So here it is. Share screen. Here. Okay. And okay, I have it's up here. This has a driver, but that doesn't illustrate the process. Here's the assembly inside of C. Okay. So notice this is an ordinary function. It's going to compute the average of numbers in an array. Okay. In pink, you'll notice this is assembly stuff in here, in the pink characters. But outside of that, it's regular C language or C++ language. You know, it's the regular stuff. So it's embedded. They don't call it embedded assembly. They call it inline assembly. So if you want to Google for it, you'll find lots of examples. And this is useful in their environment. I don't think it's the place to teach it. So the characteristics are, each line needs a prefix to tell the C++ compiler, hey, this is actually a line of assembly. It's not ordinary C++. And that's quite amazing that inside of G++, there's buried a NASM type assembler. It's inside there. It's remarkable that they did that. So when it comes to a line like this to compile, then it calls upon that NASM inside of G++ to handle it. Okay, so you should recognize stuff that we do all the time. There's an array up here. What was it called? Global array. Global array. It is. Okay. Anyways, it references stuff from outside, and you notice all the stuff we've done before. And there's a loop in here somewhere. It says start the loop here. And we should talk about CQO later. It computes the average, does an IDIV, things we've been doing. Okay, does that all work? Yeah, it should. So you get the, oh, one more thing. Remember we learned about AT&T syntax and Intel syntax, two competitors for the same, it's the same language inside. When they compile, they create the same object code, but it has different aspect at the human level. So the inside assembler defaults to AT&T unless you tell it otherwise. So this first statement is telling the assembler, no, this is not AT&T. This is going to be all Intel until I tell you otherwise. So I don't understand the statement, but I know what it does. It sets the default to be Intel syntax. And then all this is written in Intel syntax, you recognize. And then at the end, you're supposed to set it back where it came from. You return it back to AT&T syntax when you're all done with your assembly portion of it. Okay, so having said that, let's run this. I want to close this file. Just as proof that I'm not making this up. You should always ask for proof. Okay, how can I get a hold of this? How can I get a hold of this guy? Okay, here it is. Let's stretch it a little bit. Okay, ls-l and sh run.sh. Okay, it's running. It says enter up to n integers. How do you terminate? Oh, it's going to ask the question, do you have more numbers? All right, so let's enter 4 as an integer, yes. And let's enter -7 as an integer, yes. Let's enter 9, yes. And one more, 2. And I'm going to say no. What's the sum of those? For, I think it's 8. You total those 13 for, no, hold on. I can't add these negative numbers. 13, 15, subtract 7 is 8. Yes, it is 8, and there's 4 numbers. It should give us an answer of 2. Okay, the average is 2, and it exited from the system, and it's all done. No, it works nicely. I like inline assembling, but its appropriate place is on the job. It's not the place to learn it as a programmer, like we're doing in this class. Okay. So if anybody asks you about inline assembly, you'll know what they're talking about. I'm going to terminate this one. Okay. What we're going to talk about, CQO, control. Oh, control. Okay. The subject of CQO has come up yesterday and earlier today. Let's give it some attention. Can I stop the share? Okay. I've been asked a couple times, what is the meaning of that and why do we have it? And if two people are asking about it, it probably means 10 people are thinking, are concerned about it. Let's spend 10 minutes on this. So let's see, there's a whole sequence of these. Am I under the camera? See, and I hope I haven't gone muted not by me. That's not working. I'm gonna try another one. Let's try C, Q, O, and before that came C, D, Q. Before that came C, W, D, and before that came C, B, W. Okay, so the C means convert, the Q means quad, and the O means octal. So this is from quad word to octal word. This one means double, and that's quad. So this is from double word to quad word. And then you can see this is from an ordinary word to a double. And this is from a byte to a word. Or if you like to think of it as 1 byte to 2 bytes, 2 bytes converted to 4, 4 converted to 8, and 8 converted to 16. And so you think it doesn't have much of a role, but it does. In a math course, an ordinary number, 13, has magnitude, but it doesn't have a size. I guess they call it 2 digits, but they really don't care. It's a 2-digit in base 10. It's a 1-digit number in base 16. But for computer science, size does matter. And what I'm referring to is it 1 byte, or is it 2, or is it 4, or is it 8, or is it in the future there'll be 16? So if you have 13, what is 13? 1101, I think. Also known as D. So if you put 13 in register of any kind, 1101. Okay. If we had a long ago, they're antiques now. There were microprocessors of 4 bits in each register. This one would fit just nicely. Okay. That's a 4-bit 13. And if we did this, it would be an 8-bit 13. And if we went one further, so here's the 8, or 1 byte. If we went the next step higher, it would be 2 bytes. And then there would be 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 1, 1, 0, 1. That would be 13 in 2 bytes. Well, it starts to play a role when you start on to multiply and divide. Mul, imul, div, and idiv. Okay. Watch what happens. We're going to work through this and see why we need these commands. So if I had, what's 1 byte? Do we have a 1 byte register? I don't think we do. Okay, I better work with 2 byte. How do they do? What is 1 byte? Okay, here's the history of RAX. RAX is 8 bytes. EAX is 4 bytes. AX alone is 2 bytes. Oh, I know what they did. They split this one into AL and, is that the right name? A on the left, AR on the right. Can't remember. There is a one, there are 1 byte registers. They're almost never used anymore. They're just obsolete, but they do still exist. Okay, so if you had a number in, let's do it here. None of this will make any meaningful sense to a math major, but to computer science, it's sometimes important. Okay, so let's say we have a number in AX. It doesn't matter what it is, and this is a 2 byte number. Okay, but for whatever reasons, you need it to be in 4 bytes. That would be EAX. Same numeric value, mathematically, the same numeric value, but you need it in a 4 byte register. Then your source code will simply say CWD. CWD. 2 bytes is a word, and the destination is a double. That's 4 bytes. And if you just, it will take no parameters. It just stands all alone. CWD acts on AX, and it creates EAX to have the same numeric value. Got it? Okay. Then if we wanted to extend that and keep the same numeric value and create RAX, which we know is 8 bytes, then I don't want to write it here. It's CDQ. Okay. So we're going from a double to a quad. And again, there's no parameters. It just acts on EAX only. It's only, it doesn't act on any other register. And it creates RAX. Oh no, I gave you a bad information class. Oh shoot. Can I start again? What this is going to be my next follow-up. This is CDWE. This is CDQE. Let me back up, and this is Craig with the E on the end. Let me finish the story without the E. Okay. Here we start with AX, 2 bytes. Okay. And in my source code, I simply put C, that's a word, CWD. What it does is it takes DX, part of RDX. Okay, this creates, it does an extension, but it puts the high end in R, where is it, DX with AX. Uses 2 registers for the outcome. Here, can I show it in a picture? Here's RDX. Here is RAX. And that's 8 bytes, but down here, 1/4 of it, that's DX, and that's AX. Okay. So when you do this command, CWD, it takes what's here and extends it to include all of this. No, I said that wrong. I'm sorry. I still can't get it right. No, it extends it from where here, the extra part goes in here. It never touches this. The outcome is you have a 4-byte number split over 2 registers. The high order bits, most significant bits, are in DX, and the least significant are in AX. Wow, I'm having a hard time saying that. Okay, let's try. Okay. Oh. DX now and AX. I'm going to use decimal because we can see it easier. This has junk. This has a nice number in it, 17. And then you issue the command CWD. Then we still have 17, but it covers the bits in 2 of those as if they were 1. 17 is here, and it probably puts all zeros over here. And jointly, the numeric value is still 17. Okay, got it? Now we go up 1 level. Next level up is CDQ. It means we start with a double in RAX. The double, let me see. Yeah, the double is known as EAX. So it has some number. I don't know, 3017. The double in RA and RDX is known as EDX. It has some junk. We don't know what it has. Okay. Then you issue the command with no operands, CDQ, and the end result is this number is extended across here so that the complete set treated as a single number, here's EDX and EAX, is still 3017, whatever the bits are. Bits and bits, 3017. So the pair together is still numerically 3017. If this was negative, doesn't matter. It will take those -1 bits at the front and extend them across here and make it such that this bunch of bits followed by that bunch is these are 32 bits, and 32 is a 64-bit quad word with the same value that you started out with. So this is the starting value. This is the ending pair. Let's see if there's any comments. Where there's a point coming to the end of all this. If you hang on. Okay. One more. The next level up higher is CQO. That means convert from a quad to an octal. That's from 8 bytes to 8 bytes to 16 bytes. Again, it's only X on a register RAX, EAX, AX. It's all these, the A register. So we have a number in RAX, whatever it is. Big, huge number, 89,465,376, something like that. Okay. Then you issue the command CQO. Then it takes that numeric value and makes it take the form of 16 bytes spread over 2 registers, RDX and RAX. Okay. In this case, if this is positive, I have a feeling these are all zero, but at least it cleans up the junk that was there previously, and etc., all the way through the end. And you get that pair that numerically is the same number, but it's larger in size, not magnitude, size. This is a size 16 bits. Okay, you with it still? Now, why do we need this? Now, here's the answer why we need it. So it has to do with these two instructions, mol and imol. Okay. That's multiplication. This is multiplication of unsigned integers. If it's unsigned, the high order bit doesn't count as a plus or minus. The high order bit is just part of the number. If it's signed, then this is 2's complement. 2's comp really cares about the high numbered bit. It treats it as a plus or a minus. A 1 is a minus and a 0 is a plus. Okay, so if you're going to multiply two very large integers, suppose you want to multiply R14 times R15. And both numbers are like 16 trillion or more. Both of them have 18 decimal digits in each of them, or 64 binary bits in both numbers. You're going to get a huge number that won't fit in the answer register. And it won't. It'll be more, the answer will have more bits than any one register can have. And so it's going to give you a split answer. I'll show you the source statements for it. To make this multiplication, you'll move to RAX, R14. See the A? That comes back all the time. Okay. Then we're going to see, do we have to clear it? We should anyway. Division is even more clear. That takes our factor R14 and extends it over two registers. And then we say imol R15. The answer is called the product. Where is the product? The product is in RDX combined with RAX because it won't fit into RAX alone. The whole thing is 128 bits, 16 bytes, and the multiplication of those two very large integers needs that much space to store the product. Simple as that. Okay. Now, division gives it away. We're going to do division now. Division, you're going to see CQO again, and it's really mandatory. Yeah, just throw something. Okay, we're going to do this. Okay, suppose you want to do this division. You want to divide R14 by R15. They're integers. Okay, we're going to use IDiv. That's the one you use for 2's complement. 2's comp integers. You use div all by itself if it's no sign. Okay, so we're going to use IDiv. There's a sign in either one of these two, and we want to do this division. What you have to do is put it in RAX, the numerator. Now, a few lines later, we're going to do IDiv by R15. But because division is the reverse of multiplication, when this goes to do division, it looks at the double number. It looks at the double register, RDX with RAX, as one number. And if RDX has old junk in it, you do the division and you're going to get a junk answer. What we want is our number from R14 to be expressed across all 128 bits. And then IDiv will work correctly. How do you do that? CQO. Now the number in the numerator in RAX is extended as the same number across these two. And IDiv is programmed in Silicon to go to both registers and do the division into that. And you get an answer. The quotient is in RAX. UOTIENT. And at the same time, for free, you get the remainder is in RDX. Okay. I did this long ago when I was kind of young and dumb. I left this out many times, and the answers were always wrong because the division operation takes into account both registers to compute the quotient. It doesn't isolate itself only to RAX. So suppose I just do dividing some small number, 87 divided by 13. Okay. If I didn't do the CQO, I get a horribly bad answer. It just in the millions or something. And yeah, it's a debug problem. What's missing is this guy in the middle. Okay. Yeah, that's how it works. Anyway, okay. I gotta now we go to the footnote. Okay. The footnote is that page previously where I had a mistake. Okay, so here's our sequence. I like to write it in reverse order. So it's CQO, CDQ, CW, D, CBW. There. Okay. The first three have companions. CBWE, CWDE, CDQE, and this one doesn't exist. BQOE. Oh, it may someday, but it doesn't. It doesn't now. CQOE doesn't exist. Well, okay, here's what it means. Let's take the one right up here. CDQE. Okay. It says we have a double. All of these act on RAX, by the way, in some form. Okay, so we have a double in RAX. RAX is split. The low half is called EAX. The upper half doesn't have a name. But the assumption is we have a number right here. If you use the command CDQ, what it does is it expands this number, but it puts it into the expansion goes down here in EDX. Okay, there's the pair, EDX paired with EAX. Okay. Now that's what happens when you use this. Now the question is, what about CDQ with an E on the end? Here's the answer. RAX, and we starts off with this. There's a number here. EAX. And then there's unknown junk here. And then you issue the command CDQ with an E. This doesn't involve RDX anymore. This ends up creating RAX expands within itself. So you stay in, this is still here unchanged, but the expansion is over here inside the same register instead of putting it in the RDX register. So the E on the end means do the same expansion, but stay within the RAX register. There's others. If you did one of these others, it means stay within RAX. Stay within RAX. You don't bring the other one, its companion, into play. That's what the E on the end means. Okay, let's see if there's. Okay, do you remember the timing program? Oh no, it wasn't the timing program. It was the Control D program. Scanf is taking in numbers. And the practice program said, when you're done putting in numbers, press Control D. Okay. When you press Control D, scanf puts -1 in EAX, not RAX, EAX. So the register is filled in its lowest half with -1. We know -1 is 111. But this part has junk, unknown stuff. Okay. Well, you want to be able to test in your source code to see if Control D has been pressed. We want to test this piece over here. Now, my style is I don't want to work with E-type registers because it's kind of in the past history. It's not common in modern assembly. It's common in old assembly. So my style would be, let me just expand this whole number to the whole thing. That would be C, D, Q, E. And then I have a -1 in all of RAX. There's this here and there, both sides. Then I would compare RAX with -1. And I can find out if there's been a Control D pressed. If it's not Control D, then this remains a bunch of garbage over here. How do I say that? If it's not Control D, then this remains former garbage, what it used to be. You can extend it and you can still test to see if it was -1, and it won't be -1. So here's a use of that in play where you extend the number and stay in the same register. CDQ without the E, it would bring into play the RDX register, and that's too complicated. That is more complicated than this. Okay, everybody with this thing? Let's see, do I have anything more about that? How do we do that? Does this involve this involves the timing, doesn't it? No, it's kind of a side issue to it. When you're going to read the clock, LS LSCPU. No, that's a CPU. Sorry, that's a bash command. CPU ID. C. Can't even spell it. CPU ID. Okay, that's an assembly instruction. This is bash. Yeah. Okay, so we do the pair CPU ID and RDTSC. And then you remember that it stands for the first two letters are read, and the last three characters are time stamp counter. Okay, and that puts the number of bits, number of ticks, puts the number of ticks in a pair of registers EDX. There's the pair again. Those two guys go together all the time. D and A. Okay, it puts the number of ticks in those two registers. Least significant count down here, LS B for bits. Most significant up here, most significant bits. And then that looks like it's already been split, but we have to put it back together. So what did we do? We have to move one, don't move this one high, move this one to the high bits. That is shift to the left. We can't name EDX, it doesn't have a left, but we can name RDX. 32 spaces, 32 bits to the left. Now all those bits have shifted towards the left. We can add them and we get the final good number. ADD RDX, comma, EA. What am I saying? RDX. Yeah, RAX. It looks like that. Okay. And that works. In picture form, we're adding a register that's has data here and zeros here. And the other register is zeros here and data over here. So when you add them, the zeros don't have any effect, and you are smashing together the two 32-bit subregisters, and you get one final number. The final number is in RDX. That's your count of ticks. Okay. Well, class, let's see. Let's check my agenda notes. I don't see anything here. Oh, we're just about done. Did I mention the program I posted? Let's see if I, at the beginning of this hour. Oh yeah, this one. Okay, then, yeah, you should try it out. And what you do is you cover up how it got there and see if you can find the linked list in that stack dump. Especially the security people, that's what you're going to spend your life doing, is studying the inner workings of machines to see where viruses and Trojans and worms are. You're not developing new software. You're protecting your machine from intruders and attackers and all kinds of bad things. So try it out. This usually shows up on the final exam concept part. Something about a stack dump, and you'll do well if you practice it in advance. I think I've covered all the topics for today. Anybody have a question? Okay, I hope I'm not muted. And okay, so last announcement is Say we have, our test is next week, Thursday. We have 9 days. Okay. So the announcement is, Johnson is a really nice guy. He's having an SI session every Tuesday and Thursday at 5:15. I don't have his Zoom number in front of me. I should look that up. But those SI instructors form their own agenda. They don't come and ask me what should I do. They're trained to pick their own agenda. But I noticed that Johnson follows pretty closely to what these lectures do. You'll probably see him talking about these same subjects and refreshing it in your memory. That's his first name. You should drop in this afternoon and see what he does. You can come anytime, you can leave anytime, up till, when does he end? 6:30. Okay. I'm done, everybody. Anything that you have in your mind that you want to ask about? Old programs or the current program? The current program is to use indirection with GDB commands included in the input file. So I'll be here until 4 o'clock, just hanging out. If you're free to do whatever you need to do. I think you're missing out on stuff if you don't go, but if you mastered it already, you won't need kind of that helpful stuff. He does beginner topics typically. Okay, class, have a nice afternoon. I'm glad you were here with me this semester rather than somebody else. You probably thought it was a horrible struggle. But hey, I tried to show you where my enthusiasm is. This is what I like to do. So you lived with me for these 3 months. Soon, in 2 more weeks, you're going to be gone and you're going to do other higher upper division stuff, and it will really confuse you. And then you'll say, well, I used to be in holidays class, but I'm glad I'm out. Have a nice day, everybody. I'm having fun.
Thank you, Professor.
You're welcome. Have a nice day. I should put the camera back on me.